I guess most of you already know who I am and what capture is, so I'm just gonna skip on the introduction a bit. But the purpose of this seminar is to basically show you how capture works internally. So this is intended to be kind of how-to of the general flow and capture if you're interested in doing something interesting with it, if you want to do something different than the demo capturing, which is kind of the normal functionality, or if you want to fix capture and don't get how it's put together, then this seminar is probably for you. Okay. For the outline, I'll first give a brief introduction, then I'll talk some time about the basic principles behind capture, which is first the original idea behind capture, like what's this intended to do, and how I intend to accomplish this, and then I'll go into a somewhat more detailed overview, which is capture piece by piece, and I'll talk a bit about the video encoders used, how the video APIs are involved and how to capture video stuff, and about audio. And actually, the most important part about capture isn't any of this, but the timing part. But this is really, really hard to explain on slides. So I'll just try to improvise it a bit and show you. I'll give you a talk through without slides and just show you pieces of code, and hopefully that will work out. And afterwards, there will be time for questions. Okay. So first, I already said this. The idea is to show you what capture can do, how capture works, what the general idea is, and what to do if you want to do your own capture mods, if you will, and how to make your demos capture friendly. Because by now, the current version, 0.07, which is somewhere in November last year, is at a point where I'm able to capture basically most releases in 2007 that I tried, like 95% work. Maybe with some option twiddling, but it usually works. And at this point, it's really hard for me to fix each demo individually, because I now got the basic feature set covered, and the demos that don't work usually have something very specific to them, and fixing that either means breaking other demos or writing a lot of code for capture that's only really useful for one demo. So at this point, it's really a better idea to just fix your demo to work with capture instead of the other way around, at least for new demos, because it's not hard to do so. So I intend to give you a basic overview of how to make your demo capture friendly, what works, what doesn't. And finally, of course, if capture doesn't work, I'm very happy if someone can send me a patch. I'll, of course, debug it myself if I get a bug report, but as always, patch is welcome. And if I have some time afterwards, I'll just tell you about some of the more interesting bugs in demos or sound APIs and so on that I found while writing capture. Okay, first, this is a list of common misconceptions about capture that I read all the time in forums and whatever. And I just wanted to put this in front of this presentation, so even people who just skim by will get this part, because I really want to get this out. The first thing, capture is not direct 3D only. For some reason, I get this all the time that people think it's direct 3D only. No, it's not. Actually, the first versions were OpenGL only. Capture is not a screen grabber, which means it doesn't really care whatever is displayed on your screen. That's not what it looks at. You don't get any tiering if there are instant messages, pop-ups, whatever, it doesn't care. What capture does is just take the buffer that is being rendered to by the application, and just before it is submitted to the graphics API for display, it encodes this as a video. So whatever is happening on your screen isn't really interesting. You can have the window hidden, whatever, doesn't matter. You can have the window in the background, again, doesn't matter. It just grabs whatever the application is rendering, not what it's displaying. This is an important distinction. And it doesn't do anything system-wide. Everything capture does is local to the single process of the application being captured. Basically, capture works like a debugger. It modifies some small pieces of code in the application to do its magic, But there's nothing system-wide there. It's perfectly fine to capture in the background, do something else while capturing. If the demo supports it, some demos stop running when they lose focus. Obviously, in that case, you have no chance of capturing them in the background. But in principle, there's nothing that prevents you from doing this. And finally, even though you have a full codec selection screen at the front of capture, it's a bad idea, usually, to do a full quality encode directly from capture. There are 2 points to this. First, you typically want your capturing to be fast, and the modern codecs usually require you to encode the whole thing twice. Capturing is a relatively slow process, and encoding is a slow process, and you don't want to repeat the whole thing twice, and it actually gets faster if you just encode it with a fast lossless codec first, and then do a 2-pass encode on that. And more importantly, a lot of demos actually have small variations between individual runs. Like the timing is not 100% exact, or they have different random seeds. So if you try to use a 2-pass encode on that and the video material is different, it just won't work. So again, it's a better idea to just use a lossless codec for the initial capture and then do a real encode later with virtual dub or something similar. Okay, that said, the main idea behind capture. All graphics APIs that we're interested in, at least, are double buffered, which means that the application is rendering to some off-screen buffer, and then sometime later, when the rendering is done, that gets displayed to the user, either by changing the start pointer where the graphics card actually reads the screen data from, or by actually copying it over, whatever. We don't care, but the point is that we're not directly rendering to an area the user is seeing right now. Again, this is not a screen grabber, and the point is that we can intercept after the rendering to the back buffer and just try to get the contents of the back buffer before it's displayed on screen, because that's the easiest point to intercept it. And more importantly, this swap buffers call, where the buffer gets actually displayed, is a very clear indication that the target application just completed rendering one frame. So at that point, we know that something was just rendered, and it's probably a good idea to advance time somehow. Now, these functions are called differently for different APIs, so you need to handle the APIs separately. But the general idea is to intercept this one call, the swap buffers call, and if you get that one, yeah, you're basically set. That's all you need, because this is where you can grab the video and you can be sure it will work out. The trick about capture is, this part is fairly straightforward, but the trick about capture is that you can actually make time stand still for the application in between calls to swap buffers. So what capture does is basically simulate an infinitely fast CPU that is able to do any amount of work within one frame, and no time advances at all. And by the point we get to that swap buffers call, that's we have this way slower graphics card that always takes whatever 60 milliseconds or whatever to render one frame, and so this is where the time is spent. But before this call, no time changes at all. And again, we pretend that rendering also takes a fixed time. We don't care if the graphics card can render the screen in 5 milliseconds or 500. We'll just pretend the time advances in discrete steps for every single frame, and it's always the same. So it's a perfectly fixed frame rate. So why would someone want to be doing this? The original point was that I was watching the Scene.org Awards 2004 at Breakpoint 2005, and the videos they had were grabbed with fraps on a not very fast machine, and they had lots of frame drops and were recorded at the wrong frame rate, and it just looked absolutely horrible on the big screen. And I thought it should be possible to do better if you do it like this. And so this is why I started Capture. And the problem is, if you want to do this real time, like with fixed frame rate on a normal machine, the machine needs to be really, really fast, because you need a fast graphics card. It may not stall at all, and you have to have a very fast hard disk to be able to actually save that video, and it's all very equipment heavy to do this, but by removing the real-time part from the equation, it actually gets a lot easier. And because Windows demos don't actually have that many sources to get at the time, because they always have to call at some point through a very small number of different API functions that are all their possible sources for timing information. So if you get these API calls, then you can just make the application see whatever time you want to. So how to build a time machine? Again, we need to control the time as visible to the application in the target process. We do not need to change system time, whatever. We just need to intercept all the functions that the application could call to get any timing information. Now there are tons of possible time sources for a normal demo. The direct ones, which probably most Windows coders know and have used at some time or other, is get tick count, time get time, query performance counter, etc., which just give you a normal timer value that just increments over time, and you have a fixed frequency that you can query, and it'll just return you the time value. Now, hooking that is pretty easy. You just have to change the value returned, that's it. The indirect ones are like sleep, wait for single object, wait for multiple objects, all the variants, which are mainly used for synchronization, but also have a wait component to them. So like wait for this event to happen or abort after a fixed number of milliseconds. You need to intercept that one too, because it's typically used to synchronize like the video rendering thread with the audio rendering thread, and this one needs to work as well or it will break, and yeah. Then are the event-based timers, which is time set event, set timer, which is somewhat exotic API. There are not many demos that use this, but there are some of them, so you need to do that as well. And what these ones do is that you just can say, call me whatever every 50 milliseconds, or call me after a specific amount of time passed and don't do it again. And this is what these functions do, so you need to handle this as well. Then there's obviously the current play position from the sound card, which you need to control, because again, the user expects time to advance by exactly 16 milliseconds in samples between each frame in a 60 frames per second capture. So again, you need to be careful with this. You actually need to emulate the sound card for this. I'm going to get to this later. And finally, one last time source would be the CPU timestamp counter, which is the actual CPU clock cycle counter. Intercepting this one is really hard to do. You basically need to run a virtual machine monitor to actually hack this one, but because modern CPUs dynamically adjust clock frequency and the RDTSC thing is kind of unreliable for long amounts of timing anyway, because of various problems. No one actually uses this for timing in demos. They use really weird functions, like, for example, for the direct timers, some demo users get system time as file time. I didn't even know that call for timing. Whatever. But this one, actually no one uses this one, so we can just ignore it. And anyway, all these calls we have to intercept. We have to make them report consistent values, because if you have some skew between the different time sources, at the very best, it will just break. At the worst, it will crash. And it will definitely be off sync and won't work, so you need to be careful with that. Yeah, and if you do that, congratulations, you're now officially a Time Lord. You can control time, make it run backwards, whatever you want. That's all you need to do to remove the real-time part, basically. And the question is, how do we do it? Whoops, wrong slide. Yep. So how do we intercept API calls? This is where it gets interesting. If we had the source code to the demo, this would be pretty easy. You can just do a search and replace for all the calls you're interested in. Just replace the calls with your own functions that implement the functionality you need, plus frame grabbing, whatever. And then you just link with a library that replaces the system calls, and just, yeah, we have an implementation of swap buffers that grabs the current frame and then calls through to the real swap buffers function. We have an implementation of get tick count that just reports whatever value we wanted to report, and so on. So that's pretty easy. If you had the source code, or could just link with your own library, this would be pretty straightforward. But we do not have the source code, and we have to do this using the binary only, and it gets a bit more complicated than that. On Linux, where you typically use dynamic linking for the libraries, and there's this LD preload environment variable that allows you to load a library that replaces calls in other libraries before everything else. So on Linux, this is really easy to do, but this is Windows, where we don't have that functionality. And we have to get somewhat fancier than that to actually intercept the API calls and make this whole thing work. And the trick is binary instrumentation, so-called binary instrumentation. Instrumentation in general is about inserting a specific function called like whatever at the start of some function I want to get notified, and then again at the end, whatever. So I just want to get those calls to monitor whatever the application is doing, and at that point I can do something else if I want to. And since we don't have the source code, we have to patch the target program somehow. Now we could try just replacing all the calls to the functions we're interested in, but this is pretty hard to do actually. Because you have to look for the byte sequence that's the call to that function, and you just have to scan through memory, possibly megabytes of it. What do you do if there's a false positive? If it looks like a call sequence but is actually in data, then patching that would be a really bad idea. Then there are different opcodes, like call, jump, different variants. And so this whole patching the code directly thing really has a lot of problems. And even if you get this one right, then you have to worry about indirect calls, jump tables, and it just gets worse. Basically, it's something you would have to do a complete program flow analysis, and this is just not going to happen anytime soon. So the idea is to just screw all that and patch the destination functions where the application is jumping to, not the call side that actually does the call. So these are really easy to find because these are exported names. The API functions have a name, and we can just query where does that function start, where would it jump to, and we can just, if we can just patch that one function and make it route to our replacement function, then we're set. So this is the basic idea. And how does this work? Up here to the left is our swap office function, which starts with a normal prolog. If you can't read x86 assembler, just ignore it. It's not going to be important for the rest of the talk, but I want to explain it for anyone curious because this is really interesting. How do we do interception? We first have to copy the first few opcodes of the target function to a so-called trampoline function, which I'll call real swap office. What the purpose of this is will be clear pretty soon. So you copy the first few opcodes and then just do a jump to whatever comes after these few opcodes you copied. Then you write your hook function, which is the function you want to get called instead. Whenever someone in the application calls the real swap office function, then you overwrite the start of the original function with a swap office call. This is why you need to copy the first few instructions, because you actually overwrite them. And if our hook function at some point wants to call through to the real swap office function, which it typically will want to, because it probably does not know what the driver is going to do with whatever you just presented to it, then you need to call through, and you need to call this real swap office function. And this just has the instructions that we've overwritten and then jumps to the non-overwritten part of the original function. That's the basic idea. And Capture uses a library for that, which is called Detour by Microsoft Research. This does exactly this. This is the whole process. So this is what you need to do to redirect calls. This is probably one of the most important single tricks. Now there are some things you need to worry about. First, you can only call or jump to functions in the address space of your target process. So you can't just jump to a different process. This is important because we're running Capture as a separate application, and we can't just call over there. So we instead have to make sure that our code ends up in the image of the target process where it can actually get executed. And what we do is basically the same thing again. You start the target process as suspended, which means it's not running. The instruction pointer is just set at the start, at the first byte, but it does not start executing at first. Then you allocate some memory in the memory space of the target process, which you can do. As said, this is basically what a debugger does. So this is not very hard. Then you can just do this whole patching thing, like here, with the startup code, like the first few bytes in the original program, and just make a jump somewhere else. And this is somewhere else is in the memory you just allocated. Then you can put your own init code there that loads capture DLL. This is where the real magic is, this is where the real magic happens in capture. This DLL, the whole program, is just a front that literally only does these 5 steps and makes the target application load the DLL. Everything interesting actually happens inside the target application. And this is where all our code is. And then the capture DLL startup code does the rest of the initialization and intercepts the functions we're interested in and so on. And if there are virtual functions involved, like for example we have with COM interfaces, direct 3D, direct show, and so on, there's an additional complication, and that the name of the target function you're trying to intercept is not actually exported anywhere. So at this point you have to get somewhat fancier. It usually works this way, that there's some function call in the target library that allows you to create an object of this type. And then in the object there's a pointer to a so-called virtual function table, which is just a per class jump table. And that contains the addresses of the actual functions you're calling. So you need to intercept the points where these objects are being created. And once you know there's an instance of this object being created, you know where the functions that it's going to call are, and then you can detour them. That's the idea. But so with the COM interface stuff, you have to do a lot more work, which is the reason that the first versions of capture were OpenGL only. OpenGL has just single procedures, which is way easier to do, and this one is a bit more involved. It works the same way, but it's somewhat harder to get the address of the function that you actually have to redirect. Okay. Yeah. So much for the basic principles. The next point is video encoding. Video encoder stuff has a really, really simple interface. It's just a class. Basically allows us to say what's the size of the frame that we're going to write in pixels, write the frame data, set the audio format, get the audio format if you need it later, and write 1 frame's worth of audio by just passing it a buffer. That's it. This is the video encoder interface. All video encoders in capture implement this one and just work exactly the same. And there's this config dialog at the startup of capture where you can select which codec you're interested in, and this will set up an appropriate instance of this video encoder thingy and put it into this global variable encoder, and everything else works through encoder. And again, there's several implementations of this. There's a normal AVI writer. There's a different variant that uses direct show and basically doesn't really work. Sorry. There's a variant that uses the bitmap and wave file writer, which is very useful if you're only interested in grabbing the audio, because then you get a nice wave file of your demo, and is not that useful if you need the frames, because storing 10,000s of files, of bitmap files for individual frames normally isn't a very good idea performance-wise. But if you just need single frames, it usually works. And again, this was the first thing I implemented it because it's the easiest. Okay, so the actual implementation details are pretty boring and somewhat tedious in the case of direct show, which just means that I won't talk about this. So basically, in the capture source code, I hope you can recognize this, all these different modules, the video encoder ones, and this one is new. This is not yet in the released version. We'll get this soon, hopefully. All these implement this video encoder interface, do nothing else. So that's already pretty much half the amount of stuff, no, not really, that we have to look at. So this is a lot of code that basically always does the same thing in different variants. Next one. This is somewhat more interesting. The video APIs. How do we actually do the frame grabbing? The example here will be OpenGL, again, because it's easier to redirect. The others work similarly. And the basic flows is outlined in the example I gave earlier. And you need to intercept the swap buffers function, obviously, and some functions that OpenGL applications might be calling. For example, change display settings, which a lot of OpenGL applications use to set up a full screen mode. You need to intercept this one. There's WGL create context, WGL create context, which is the function that it always ends up calling to set up a rendering context. We actually need to keep track of the different rendering contexts the application has, and WGL make current, which selects the current rendering context, and so on. Now, there are different variants of this change display settings functions, but they all end up calling change display settings X. So you only have to intercept this one, and because the code in the actual implementation of OpenGL will at some point just set up the parameters correctly for change display settings X and call through, you really only have to intercept this one. This is, of course, nice in this particular case because it saves some amount of work, but it also means, it nicely shows a general problem with the hooking individual functions. Whenever you hook functions, everyone else in that process ends up being redirected. So whatever you do, especially with the thread synchronization stuff, you better make damn sure that what you're doing is general enough to work even when someone you're not expecting to call uses it. For example, this is one of the main problems, or used to be one of the main problems, with the early versions of the direct show encoder, which internally creates a bunch of threads, like 5 or so. There's very fancy synchronization stuff in between them, and if you get any detail of the synchronization stuff wrong, it just breaks, crashes, whatever. So you have to make sure that any function you intercept, except for the returning different time thing and so on, behaves exactly like the application would expect. And this is not as easy to do as it sounds, because a lot of applications have really, really badly written code in them, actually. And most Windows API functions will not crash if you call them with literally random pointers, or 0 pointers, or whatever that you're supposed to write to. And applications do this all the time, and any code you write needs to be able to handle this, or again it will crash. So this is more trickier than it sounds, actually. And yeah, why am I tracking rendering contexts? The users will call the swap buffers functions with the display context, but they need to know which rendering context belongs to that display context and make it active if it's not active already. The reason for this is that people may have different rendering contexts created, p-buffers and so on, and we're not certain, we can't be certain that at the point that the application called swap buffers, the right video context to grab from is actually set, which means we really have to make sure that we track where everything is so we know where to grab it from. And this particular type of bookkeeping is specific to OpenGL, but other APIs have similar problems. You always, for every API, half of the code you write ends up being bookkeeping, because you need to map something that you have to the value you actually would need. So this is somewhat annoying, but yeah, you can't help it. And for swap buffers, again, this just grabs the actual frame data, in the case of OpenGL, via glread pixels, then encodes it by passing it to the encoder, and then calls this magic next frame function, which just says this frame is completed, advance time, process audio, and so on. And the other APIs all work similarly. Audio, this is actually a lot harder to do than video, because unlike graphics cards, which just render as fast as they can and update whenever you want them to, as early as possible, sound cards play at a fixed rate, say 44.1 kilohertz. And you can't just say, well, slow this down, I'm not yet done with the frame, and you don't get to the recorded buffer that easily anyway, because it's being mixed internally in the sound card, and you just have no way of getting the output of that back, at least on some sound cards. Newer cards actually allow you to capture the final mix, but a lot of older sound cards don't, so you can't rely on it. And the best bet in this case is just to virtualize the audio completely. So this means you actually have to implement the whole sound API that you're interested in, which is obviously a major pain, but you actually need to implement this to make sure the synchronization stuff works out. And this, which basically means that you have to do a working implementation of at least the most important features of direct sound, the Windows multimedia and waveout stuff. And again, audio is a time source, so it needs to be synchronized. You need to make sure you write everything out in time and so on. So this is, again, somewhat tricky. Actually, audio is trickier than video in this particular case. And yeah, some more stuff about audio APIs. First, we have to handle the ring buffer ourselves. This is just a ring buffer that's being played in loop usually. Whether that's internally or the application does it directly, doesn't matter. But we need to consume audio in appropriately sized blocks each frame, like whatever, a 16 millisecond block of audio, and we just consume that each time we've got something rendered. And again, as with the graphic stuff, the play timer only advances between frames. So this timer value will change at exactly the moment you call swap buffers. And this, also already said, this is way more difficult and annoying than video capturing, because you need to implement the whole API. You need to do it somewhat faithfully. I skip over some of the more unimportant aspects of direct sound, like playing multiple buffers at the same time, for example, because you don't actually need it for demos, which usually just have one fixed soundtrack that they're playing. And so you can skip a lot of it. You don't need to write a mixer yourself and so on, but it's still a lot of code. The audio stuff is more code than any single, and than any 2 or 3 implementations of the video stuff. So this is really a lot of code you need to write there, but yeah, it simply can't be helped. And then this next frame function, which does the timing stuff, which I already mentioned, calls next frame sound, which just copies the data over from whatever buffer the application is writing to, encodes it into the video file, and yeah, then we have it encoded. The audio format changes. This usually happens, for example, when demos have a setup dialog and allow you to set up sound settings and so on. Some actually seem to create sound context at that moment in time to allow you to tweak with the settings. And the problem is, this is a challenge, because once you start encoding, you have to specify the audio format you're going to use at the beginning and then stick with it. And so capture just ends up using whatever format which was first set in the particular demo, resamples to that format if it later changes, so the audio format is the same throughout the file, which is not optimal quality-wise, especially because the resampler is decent but not great. So this is again something you might want to watch out for. That in general, if you can avoid it, don't do it. Okay, now for a small demo of capture. Small disclaimer: this version stopped working today for no discernible reason. It worked just fine on the same machine 2 days ago. Didn't change a thing. No idea. So I'm just going to use the bitmap and wave file writer that I just advised you not to use, and only do a short capture, so you can see it in action. Okay. Yeah. This is just default settings. Okay. So this is how it typically looks. As said, it's pretty slow because it's writing a lot of files. Okay, I think I'll just abort there. And this is the audio file. And I'll just do a slideshow in parallel. Okay, I think you get the general idea. Now, more interesting part about this demo is when you want to debug capture, because I assume, oh, by the way, we've now covered all the video stuff as well, because this, again, always does the same thing. So there's actually not much left. We got the sound covered. Main is just initialization stuff. The video encoder and audio assembling stuff is basically boilerplate code. So there's really not much left. The only interesting module left is timing, but it's actually kind of instructive to see how it works out with Capture if you're just fiddling with it and trying to debug a demo that doesn't run. So I'm going to show you how this is going to look in the debugger if you want to fix a problem. So I'm going to start Capture in a debug build. Yay, and the build fails. This should be easy. Yep. Okay, so this is a debug build of Capture with and started with the debugger running. And I'm going to do the same thing again, but this time it's somewhat different, because at this point, once the demo is actually started, you get this message from Capture that says, please attach debugger now. And this is the point where you have to go here. As said, this all happens in a different process. And debug the target application. So once that's done, again, you get a status message from debugger, which tells you that the debugger is now attached, and you can set, for example, any breakpoints you want to. So this is what you need for debugging, because now you can just set breakpoints in whatever code you seem to be debugging. I'll just use the OpenGL swap buffer stuff. Okay. So this is the code that will get called when the application actually calls swap buffers. And now that's set up, you just confirm this dialog box, and the application does whatever, gives you this screen requester and so on. And then sometime later, you get this interception. This is somewhere deep into the call stack. You see this is actually being called from GDI, which is being called from the demo, which is being called from fmod, which is again being called from the demo. So, and at some point here, someone called the query performance stuff. So the problem here is you have a lot of unknown code down there that you have to debug, which is what makes the whole debugging thing kind of a pain. But still, this is set up to make it as similar to debugging your own application as possible. And you can just do single step now through whatever your application is doing. So yeah, if you're interested in fixing bugs with Capture, I think it's important to know that there's actually really decent debugger support in case there are any problems. So this is the debugging API, and I just wanted to show that because I think not many people who have looked at the code actually grasp this. But this is important because if you don't know this and you don't know how to debug Capture, it's going to be a nightmare. Okay. Yeah, I'm just going to abort it. Yeah. So much for the demo. Yeah, if I have time, I just got a slide saying I have about 10 minutes left. I'm going to reserve 5 minutes for question, but which means I have at least 5 minutes of talking that I can do, which is nice, because there's actually a lot of interesting issues you notice when doing a video capturing application. The one most unexpected thing I found, does any of you use fmod for sound, the fmod API? Good choice. Because, for example, most MFX, synesthetics, whatever demos end up using this. And the interesting point is, I just found this out when debugging Capture, but it happens without Capture as well. You just normally don't notice it, unless you've seen the effect. Capture only updates its internal sound timer that you can query and ask, like, where's the sound at if you want to do syncing. It only updates that about, 45 times a second. So basically, if you're syncing your rendering to fmod, you're not going to get more than actual 45 frames per second. You might render more frames, but they'll be identical. And I asked Firelight about this, whether this was intended behavior, or if he wanted to fix it, and he said, no, this is just because they're all stupid and they're not supposed to use the audio source for synchronizing, so I made sure it was coarse enough. So basically, if you are here right now, if you end up seeing this on the stream or watching the video later, please, everyone who's using Fmod, write a mail to Firelight, tell him to shut the fuck up and fix this bug, finally. Because it really, it has 4K buffers. The actual frequency depends on the sound frequency you're playing. It's 45 frames per second max if you're using 44.1 kilohertz. If you're only using 22.05 kilohertz, the maximum update frequency you get is 21 frames per second. And at 48 kilohertz is somewhat better, but it's really, it's completely unnecessary, and it just leads to all kinds of weird problems that you only notice when looking at these captures. So please, Fmod users, you now know this. If you wonder why a demo looks kind of choppy when being captured, it's definitely not my error. I cross-checked several times. I don't have the test application here, but this really actually happens in your Toggle application too. You probably haven't noticed, but you will when you single step through the video frame by frame to notice, why is this frame here doubled? So please get the word out. This is Firelight's fault, not mine. And another sound system related problem, I think I can just show this. Just kill the process. I just stopped debugging, and it doesn't like that if it's just inside the process. So again, there's this somewhat inappropriately named field called Fairlight hack. This actually has nothing to do with Fairlight. This, as I later found out, I didn't know what caused it. This has to do with the base sound system, which allows you to compute the audio latency and then later compensate for it. And it just calculates that and adjusts the time value. And the problem is, if you use the base sound system, the demo is going to hang at the start, because it tries to calibrate this thing, and it does this by running in a loop, waiting for time to change. And because there's not any swap buffers calls or anything inside there, time is not going to change. Never. So it hangs there in an infinite loop. And there's a workaround for the specific problem, and that's this Fairlight hack. I'll probably rename this to something more useful in the next version, now that I know what causes it. But again, if you're using base, you should be aware of this. And actually about the timing stuff, when I just said that the timer will never advance, I lied, because there's some demos that do busy waits at some point or other. Busy waits are where you're not calling or rendering anything in between, are the main reason for capture-related problems in any demos. And I figured out a way later to do the frame skip stuff, to do automatic frame skip. So whenever an application seems to be busy waiting for more than 1 second on the first frame, because it usually happens on the first frame when it tries to synchronize audio with video, or at other frames for more than half a second, you can just change the values, then it will automatically advance the frame no matter what and behave basically like a normal screen capture program that just advances time normally until the application catches up. The problem is that this limits the amount of time your system has to render frames. So if your card is really, really slow and doesn't even manage 2 frames per second, then this delay is going to be too little. But I don't think this is a practical issue with most demos. So again, if you have demos, if you have problems with demos, this is probably a useful option to know of. Okay, now I didn't get to talk about the timing stuff a lot. But again, I really don't know what to say, because it's basically just a lot of code that's kind of intricate, but there's no point explaining it really, because while fixing the rest of capture and modifying it is relatively easy, the timing stuff is something I really advise you not to touch, because it's it has all kinds of weird side effects if you touch that code, so basically don't. And finally, some example of why I would be telling you all this. People have successfully modified capture in the past and done some interesting things with it. For example, Reptile of Astradia did a version that just captures at 4 times the frame rate and then just averages 4 consecutive frames together to produce a motion blurred version of the demo from the video, which is kind of neat thing to do, and again, just works with any demo you can capture. So the point I'm saying this, I might actually get to fix the fmod problems inside capture for demos being captured that use fmod. Might figure it out. I have some ideas, but I'm not sure whether that works out. And so we're basically at a point where capture is becoming close to actually capture the demos being better than they look in real life. And I'd like to continue this trend if possible. So if you have any neat ideas or suggestions or whatever, again, just send patches my way. And if it doesn't screw up something else, I'll probably put it in. Yeah, questions? No questions? Yeah.
Have you tested capturing applications running on the .NET framework?
No.
We've made some demos using .NET framework, and although I haven't captured anything myself, people of our group have, and they have encountered some problems. I'm not sure what they are, but
well, in theory, it should work because it intercepts the API functions that the .NET Framework runtime should eventually end up using. But there's it might use some undocumented functions as well. I don't know. I haven't looked into it. But it's probably some weird interaction problem. If you can send me a reproduce, I just have a look at it. Just email it to me. Email address is on the last slide. And yeah, I don't think there's any reason why it couldn't work in principle, but I can't tell you why it fucks up right off the top of my head. Yeah. Any other questions? No one? Everyone happy? Okay. Yeah. Yeah. Thank you. Yeah, my email address and the capture homepage, which you probably know already, are up there, but I'll put it up. Well, I'll put up the slides. Yeah, probably after breakpoint, when I'm not as dead as I am now. And I'll also put some links to the probably harder to find libraries. Actually, the version of the tool I'm using is not linked from the main editor page anymore, but it's still on the Microsoft page. So I'll just try and find that link and again post it somewhere, because it's becoming harder and harder to compile capture. Again, in the new versions of the Direct3D SDK, they just dropped the Direct3D 8 support. So if you use the new Direct3D versions, you either have to remove Direct3D 8 support from capture or get the libraries from elsewhere. So again, I'll try to figure out this, because I really want to make sure that people can compile it if they want to. And here's some links to video codecs and video tools you might want to use if you're capturing stuff. Yeah, that's it.